So welcome to our fifth talk for the colloquium on artificial intelligence, research and optimization. Today we have Andy Hock from Cerebras Systems, and he will talk about AI research and optimization at WaferScale. And before he starts his talk, I will read his bio so you know a little bit more about him, and then we can listen to an interesting talk. So Dr. Andy Hock is the Vice President of Product at Cerebras. Andy came to Cerebras from Google, where he led data analytics product for the Terra Bella project, using deep learning and AI to create useful data for maps and enterprise applications from satellite imagery. Computation speed was a problem for this work, and at Cerebras, Andy saw an opportunity to help to deliver the right compute solution for deep learning and AI. Before Google, Andy was a senior scientist and senior technical program manager at Arid Associates, where he led research for image processing algorithm development. He has a PhD in geophysics and space physics from UCLA and a bachelor in astronomy physics from Colgate University. So welcome, Andy, and we're looking forward to your nice talk.
Thank you for the kind introduction, Patrick, and thanks to the university and department for hosting this colloquium series. Before the talk began, we were discussing just how timely this topic is of AI research and optimization. In particular, that we see rapid growth in compute and memory demands for neural network training and inference for AI applications, as well as growing demands for compute in HPC, both for traditional physics-based modeling and simulation, and HPC at the convergence of AI. And there are both algorithmic as well as computational methods that are emerging to meet this rapidly growing demand. So I'm going to talk to you today about one such approach to meet these growing computational demands in a new type of processor, a new class of computer system that we have developed at Cerebras Systems. In the talk today, I'll introduce Cerebras. I'll also share a little perspective on our view of the compute challenge for AI and HPC. I'll talk a little bit about the technology and the product that we've developed at Cerebras, and then share some insight and some use case stories from recent applications using our system for both AI and HPC. So hopefully that cross-section provides you some insight into what we're doing, and maybe gives rise to some ideas about how we may be able to work together. Before I go forward with the slides, though, let me just once again say how excited I am to be here. As you heard from Patrick, my own background is in fundamental research for scientific applications, and I think that there's tremendous potential in that field for applied AI methods, and so very much looking forward to perhaps another opportunity that we may have to learn more about your work and how we can accelerate that together. And last but not least, my only regret for this talk is that I'm not able to do it in person. I wish we were able to do more of these in person. And I'm sure many of you have been in all too many Zoom meetings these days. But even more so for this talk, I make an annual pilgrimage to the fair state of Louisiana, one of my favorite cities in the world, New Orleans. I miss the food, I miss the people, I miss the culture, I miss visiting LSU. And so I do hope that there's an opportunity for me to come down, not just to New Orleans, but also to Baton Rouge and visit sometime in person. I miss it like crazy. And so I hope you guys enjoy the talk. So let me begin by saying a little bit about our company, Cerebras Systems, and the challenge of AI compute. Cerebras is an AI computer systems company. We're based in Silicon Valley. We were founded in 2016. Our founding team is a group of innovative and experienced chip architects, processor designers, computer systems engineers, and technology and business leaders that have been designing and building and delivering high performance computing solutions into data centers for more than 20 years. We gathered a team around us, not just to make an incremental step improvement on existing processor technology, but to develop a fundamentally new processor architecture to accelerate what we saw as the most important computational work of a generation by orders of magnitude beyond what's possible with legacy general purpose processors like GPU or CPU. And in so doing, transform the compute landscape by bringing a new device and new processor architecture to market that could radically accelerate artificial intelligence. With that big vision and experienced leadership team, we've been fortunate enough over the subsequent years to have strong investment from some of the Valley's luminary technology investors. And we've grown the company since 2016 to now more than 290 world-class engineers, not just in hardware, in chip design and system design, but also in software for compiler and microcode development, all the way up to integration with ML and other programming frameworks, as well as a department of applied and pure ML researchers who are looking into new algorithmic methods, new types of neural networks to accelerate AI compute at scale on our platform. And our thesis is quite straightforward. So I'll illustrate this in the subsequent slides. And I think this first message is of no surprise to this audience. That is that whether it's for scientific research or commercial applications, computer vision or language, supervised or reinforcement learning, AI has massive potential to change the way that we make decisions in our daily lives, interpret data, or model and simulate the real world. But it's fundamentally compute limited today. The primary symptom of that compute limitation is that state-of-the-art deep learning models simply take too long to train on real-world data sets, and trained models process data too slowly in production to be able to process the very large data sets that are common for scientific and research applications, as well as those in commercial industry. So why is that? At a fundamental level, one of the challenges, of course, is the work that we ask of the underlying processor. Deep learning is not graphics processing. It's not database management. It's a fundamentally different workload, right? It's got massive computational requirements, billions to trillions of compute ops per input data sample, and millions and billions of input data samples per training epoch. So table stakes for deep learning compute is often at the petaflop to exaflop scale. The memory footprint is also significant. We have gigabytes of weights for very large models and data sets that are measured in terabytes or larger. And last but not least, deep learning also requires high bandwidth communication. Neural networks for deep learning are often multiple layers whose operations and layers communicate over various topologies. So we need high bandwidth communication and high bandwidth memory, as well as massive compute. And this combination of factors, when applied to today's infrastructure, often leads to days or weeks of training time. So that's a significant challenge for research productivity. This slide is an oldie, but a goodie in my book. It's from Jeff Dean, one of the founders of Google Brain, now Google Research. I think it articulates pretty well the impact of long training times or long compute times on research productivity in AI. For models that take months to train, probably won't even try. Those we may run one or two experiments on those, but they require so much compute and so much time. They're too expensive and many problems simply go unaddressed at that scale. If compute times take 1 to 4 weeks for a model, we see this fairly often, but really only the highest value experiments get run. Much prototyping is done with smaller models and smaller data sets, and then maybe we run one or two experiments with these larger models. Really impedes progress and takes away from the interactive hypothesis testing nature of scientific research that we'd like to see. 1 to 4 days is a time scale that many of us are familiar with in scientific research, algorithm development, modeling, and simulation. If I can set my model to run overnight and come back in the morning and check on the results, or if I can set my model to run over a long weekend, maybe go hiking or camping or skiing and then come back and check on the results, that's a fairly familiar cadence for scientific researchers. It's tolerable, but we're really replacing interactive hypothesis testing by running many experiments in parallel, right? Maybe I run multiple models over those timescales and then come back and check on the answers. Where we really like to be is not in days or weeks or months of compute time, but rather in minutes or hours. That's where research can be really interactive. And the challenge of compute requirements for deep learning is growing. Before it gets better, we have to acknowledge that it's actually becoming even more challenging. The chart on the right is from OpenAI, published in 2018. They did a study of the compute requirements for the largest AI training tasks between the years of 2012 and 2018. And you'll see in that chart some fairly familiar names, ranging from AlexNet in the early part of that period to AlphaGo in the later part of that period. And what this plot shows is that during that period from 2012 to 2018, the compute requirements for the largest AI training tasks increased by 300,000x, at an exponential rate that actually is faster than Moore's law. What this tells us is not only are the compute requirements for deep learning growing, but they're actually growing at a rate that is, by some measures, faster than traditional processor technologies can keep up. In addition to models growing larger, we also acknowledge that data sets are growing rapidly. They're large and they're often sparse. Existing processors were largely built for dense computations and really weren't fundamentally built for deep learning. Tremendous progress has been made over the past 3, 6, 10 plus years by scaling out compute to meet the demands of deep learning and other workloads by clustering many small discrete processors in a data center, similar to that shown at the right. But these have some challenges, particularly for deep learning. Number one, those individual general purpose processors weren't built to execute the neural network computation efficiently. Their compute cores and their silicon area are often designed for general purpose work that may involve higher numeric precision or specific functional units to processes like graphics, ray tracing. So their silicon goes underutilized, which is the primary resource that chip designers have. Additionally, those small general purpose processors weren't built for high bandwidth processor to processor communication. In order for data to be exchanged between discrete processors on different servers in a scale out architecture like that shown on the right, data often has to go from the processor core through memory, out through a PCIe bus, over a network interconnect, over copper or fiber cabling, into an adjacent server, and then back over a bus memory to another processor. So these processors weren't really built for processor to processor communication, which is a strong requirement for neural network computing. Additionally, scaling just isn't efficient or particularly easy over large scale out clusters. We can add more and more processors And indeed, we have seen significant reduction in wall clock training time for large models in cluster deployments. But that reduction in wall clock training time isn't linear with the number of processors we add. So if you want to go 100 times faster, you can't simply add 100 times as many, say, GPUs. There's sublinear scaling, and this is particularly impactful for some very large models. So silicon goes underutilized, and we don't see a linear reduction in training time for processors that we add, which also has costs in terms of energy efficiency. And last but not least, from a programming standpoint, figuring out how to distribute my large training or inference task over tens or even hundreds of discrete individual processors is getting easier, but it's certainly not straightforward. So these scale out implementations are challenging to program. And as a researcher, if I want to do things like change my data set, change my hyperparameters, or change my network topology overall for a deep learning problem, I may have to go back to the drawing board and spend days or weeks of time ML engineering to figure out how to orchestrate the cluster of discrete processors and communication overheads. So I'll illustrate this, the practical impact of this challenge through the lens of state-of-the-art natural language processing models. So what I show here in the chart on the left is a plot of the memory and compute requirements for state-of-the-art NLP models in terms of total training compute petaflop days and the model memory requirement in gigabytes. In 2018, state-of-the-art language models were the attention-based models like BERT that are used for problems like text classification to power applications like search, question and answering, or named entity recognition. BERT base and BERT large, shown here on the chart, are on the order of a couple of gigabytes of memory and a couple of petaflop days of compute. Just 1 year later, the models GPT-2 and Megatron had been introduced by OpenAI and NVIDIA, respectively. And you can see we're now in the domain of on the order of hundreds of gigabytes of memory and about 100 petaflop days of compute. What this translates into in just 12 months is Megatron, for example, takes 10 days to train on over 500 GPUs. So we're starting to get well beyond what might be a single server or a modest cluster of compute. Just 1 year later, once again, the trend continues. June 2020, we see the introduction of TNLG, T5, GPT-3 from OpenAI, the landmark language model, and a trillion parameter model from Microsoft. Among those, GPT-3, for example, takes over 116 days to train on 1,024 V100 GPUs. So indeed, the field is making incredible progress by building larger models that have greater representational capacity, but the memory and compute demands are growing exponentially. And we're now at the point where these models are already too big for the vast majority of organizations, be they research organizations in public sector or commercial sector, industrial companies, or indeed academic departments. And the models continue to grow. So in order to address this, we need not only more compute, but we need more flexible compute that can employ smarter algorithms, smarter methods for more efficient learning, so that we can build not just bigger models, but models that are smarter and more parameter efficient, leverage, for example, weight or activation sparsity. And we need support for much, much larger models and inputs. We're well beyond the days of ImageNet, image resolutions, when we start talking about applications, for example, in large area imaging for astronomy or remote sensing, video processing, or state-of-the-art medical imaging. We need larger inputs. And we in particular at Cerebras would like to see world-class AI compute resources to be able to run such state-of-the-art models in the hands of more users and more organizations to democratize the availability of world-class AI compute. And this is what we really intend to build and bring to the market and put into your hands. In order to achieve this acceleration and scale and vision, we need a fundamentally new compute solution to accelerate deep learning. So in the following slides, I introduce what we have built. Our solution has three components, fundamentally: a processor, a system, and software. At the heart of our machine and our solution is a processor that we call the Wafer-Scale Engine. This is the world's largest computer chip. It is 8.5 by 8.5 inches of unbroken silicon with 400,000 individually programmable compute cores. Each one of those cores has 48 kilobytes of local SRAM memory uniformly distributed across the wafer for a total of 18 gigabytes of on-chip SRAM. It's all accessible within a single clock cycle from its associated core. And each one of those 400,000 cores is directly connected to its four nearest neighbors over silicon by a high bandwidth, low latency network on chip. The data flow traffic between those cores is fully configurable in software at compile time. So think of this device as a cluster of flexible, programmable, sparse linear algebra compute engines, all on a single chip. I like this figure because it shows the drastic physical scale of innovation that the Wafer-Scale Engine represents. On the right, we show the largest chip built before the Wafer-Scale Engine. That's the NVIDIA Volta V100 GPU. It's an impressive engine in its own right, 54 billion transistors, about the size of a postage stamp. On the left is our Wafer-Scale Engine. You can see by comparison, we're 1.2 trillion transistors and about the size of a dinner plate. By bringing together the compute resources of a cluster on a single chip, we're able to achieve far greater performance. So it's not really the physical size that is the metric that matters, but it's what that conveys in terms of resources that can be directed at accelerating your AI or HPC workload, namely compute cores, on-chip memory, memory bandwidth, and fabric bandwidth. So here in this chart, we illustrate the Cerebras Wafer-Scale Engine compared now to NVIDIA's latest A100 GPU in terms of those metrics that are most important for deep learning compute. Indeed, we're far larger, 56 times the area. But what that translates to is more than 54 times the number of compute cores. And you can think of all of our compute cores as the moral equivalent of a tensor core, right? All of our cores are designed from the ground up to be flexible and programmable, but to accelerate tensor-based sparse linear algebra operations at the core level. So we're really built for this work. We're not built for general purpose processing in that sense. On-chip memory, we have 450 times the on-chip memory. So we can hold your entire model in state on one chip rather than processing layer by layer. Memory bandwidth, because all of our memory is on-chip SRAM, we have more than 5,000 times the memory bandwidth and more than 20,000 times the communication bandwidth between processors than is possible on a GPU. All of this allows us to execute training and inference workloads and HPC workloads, not just faster, but more efficiently. So our architecture is really optimized for AI and HPC. You can think of it as a 400,000 core, massive sparse linear algebra engine, able to execute very fine-grained parallelism. It's a programmable core with a large bank of very fast on-chip SRAM, a software configurable 2D interconnect on chip. The routing is established at compile time. Send and receive is included in the instruction set for very efficient execution. A little bit more on those just in a few slides. Our memory architecture is distinct from a traditional von Neumann architecture in a traditional C or GPU sense. Traditional chip architecture would have a bank of DRAM separated from the compute units and connected over a relatively narrow bandwidth link. This is punishingly slow for many neural network operations. And so in our design, we've opted to put all the memory close to compute. So all of our memory is a single level hierarchy of on-chip SRAM uniformly distributed amongst the cores and across our physical wafer. So it allows us to load and execute an entire model on the chip at one time. The cores are identical. You can think of this as a homogeneous, uniform 2D array of identical cores. At the core level, they are data flow triggered, single instruction, multiple data processors. No OS runs on the machine. Everything in our machine is orchestrated by standard CPU servers that support our system as a network attached accelerator. The latency is extraordinarily low. And because we're a data flow triggered machine, our cores at the individual core level can also detect and avoid multiply by zero operations, meaning we can execute sparse workloads far more efficiently and quickly than a dense engine like a GPU, which will multiply by zero, wasting cycles and time on operations that aren't driving your network towards convergence. The on-chip network is fully configurable in software to support arbitrary communication patterns. The figure at the right is a screenshot of one of our user interfaces that shows the logical data flow routing on our wafer for the model VGG19, which is actually quite a small model for our chip, but it's a 19-layer convolutional neural network for computer vision applications. At this resolution, the routing actually shows up pretty well, but what you're looking at is essentially the data flow traffic pattern of the input data from the edges of the chip through multiple layers of the network on the chip. So this, our software configures this routing at compile time. The routing itself is optimized for high throughput to achieve efficient high performance on neural network training and inference problems. So that's the chip and the WaferScale engine. Once we arrived on this large form factor, high performance WaferScale processor as the heart of our deep learning solution, we had to fundamentally rethink system engineering, packaging, power, cooling that massive engine. We couldn't simply put the WaferScale processor into a laptop or a desktop or even a standard 1U data center server. So our systems engineering team conceived of the solution shown here. We call this the Cerebus CS1. This is our flagship product, is what we are building and delivering and deploying into data centers today to accelerate AI and HPC research. And this single system is the most powerful single node AI computer system available today. Each one of the CS1s is powered by one of those big WaferScale engines. It is built to easily deploy into a standard data center rack. It's 15 RU tall, or about 26 inches tall, the size of a large hotel room mini fridge or a dorm room mini fridge. We take standard power connections and standard 100 gigabit Ethernet data connections to adjacent infrastructure. Because our processor has high data bandwidth demands and processes a lot of data quickly, we have 12 100 gigabit Ethernet connections for a total aggregate I/O at the system level of 1.2 terabits per second of data. In this one machine, we typically see the performance equivalent of many tens to even hundreds, or in some cases, 1,000 or more GPUs. So in this single machine, less than 1 rack in size, we can deliver the performance that's the equivalent of many racks of traditional general purpose processors and servers. For those of you in the audience that are in the data science or ML research groups, this is a natural point to ask. That seems like really exciting hardware, but how do I program it? For that, our team has invested significantly in building a software platform that makes the CS1 and the WaferScale Engine easy to use by meeting you where you work in Python-based open-sourced ML frameworks like TensorFlow and Python. So the short answer is you program our system with a framework like TensorFlow, just as you would a GPU or a TPU or another AI accelerator. This happens in our software stack in 4 basic steps. First, you express your model in your framework, say TensorFlow, and at compile time, our software intercepts, extracts, and translates your training or inference program into an intermediate representation of the compute graph that we call LAIR. Because we're mostly engineers and scientists and not as many marketing people, LAIR just stands for Linear Algebra Intermediate Representation. It describes the compute operations and communication operations of your training or inference program to the subsequent components of our compiler stack. Our software then automatically matches a high-performance compute kernel to each and every layer of your neural network. And for us, these kernels are high-performance microcode implementations of common deep learning operations like convolution or attention or softmax. So we have a library of high-performance kernels, and our software matches one of those to each and every layer of your compute graph, and then allocates automatically compute and memory on the WaferScale engine for each and every layer of your program, essentially converting your n-layer neural network into an n-stage data flow pipeline, all that resides on our chip. We run that as an executable on our device. You can think of our machine once again as a network attached accelerator. So this entire software stack lives and runs on a standard x86 commodity CPU server, runs in a standard container alongside standard distribution of your ML framework. So from the user standpoint, you simply log into a host node as you would for any other accelerator resource, express your model in the standard semantics of your ML framework like TensorFlow. And our software does the rest in terms of extracting and compiling that job and running it on the CS1. So this entire stack makes the system programmable with today's ML frameworks through a library of high-performance deep learning operations. And we're also building a set of lower-level APIs and a software development kit for users that want to write their own custom computing operations. We're seeing a lot of excitement in this kernel software development kit for HPC applications, where a user may want to encode a particular algorithm for data processing or modeling and simulation to run on our full fabric of 400,000 cores. And maybe they're not doing a traditional deep learning training or inference task. So we're building a lower level software development kit for users who either want to write custom kernels for deep learning or for other applications like HPC. The software, together with our chip and our system, give you as a user access to a cluster scale AI compute resource, but with the programming ease of a single node. This represents a huge advantage to many of our users who have seen not only significant acceleration in compute wall clock time for training and for inference, but also a reduction in the amount of time it takes them to program and do hyperparameter search, optimization, and performance tuning on the device, because they no longer have to think about, take the extra step of distributing their workload over many discrete nodes. They can simply scale up performance within a single node and keep the programming of their network and their problem at that same single node level. So then to translate in a little bit into the practical impact of this and what we've been seeing with some of our customers. First, the practical value to users of, say, tens or even hundreds of GPU equivalent performance fundamentally translates into training models in hours or days rather than days or weeks or longer. And from a researcher standpoint, what that translates into is an ability to test more ideas per unit time, ask and answer more questions, and reduce the cost of curiosity. Or equivalently, take the same model that I have been working with and bring much, much larger data sets to that model so that my model better reflects the real world phenomena that I'm trying to capture. For inference, our machine is uniquely well suited to support inference of very large models at high throughput and low latency down to batch size 1, because we can compile an entire model onto the chip at one time and run it as a pipeline. We can achieve full utilization down to very, very low batch and run large models at low latency to achieve answers to your questions faster. Not only did we build the machine to train today's models faster, but we also built the machine fundamentally as a platform for research to explore ML methods and networks that may not be practical to implement or even possible on today's distributed architectures. A couple of more concrete examples. We've been fortunate to have a very good working relationship and partnership with the Department of Energy since relatively early in our company's history. One of our first deployments was to Argonne National Laboratory outside of Chicago. Researchers at Argonne are using our machine today in their data center for problems ranging from COVID-19 research to studying the properties of gravitational waves for fundamental astrophysics, to models that help them understand the potential response of cancer treating drugs. In particular, for that last example, they have a cancer drug response prediction model that's running many hundreds of times faster on our system than it does on a conventional GPU. And as their associate director, Rick Stevens, who some of you may know, says here, what that really means is that their research teams are able to make discoveries in the timescale of months rather than years. But it's not just in government and sort of basic research. We've also been fortunate to establish some really strong partnerships in the commercial space. One of those is with GlaxoSmithKline, who's also doing work in drug development and life sciences research. At GSK, Kim Branson, who's quoted here, and his team of AI researchers are using large graph neural networks, as well as large language models like BERT or GPT for drug discovery and biotechnology research. And here, their interest was not just in accelerating training and inference on those models, but in inventing new types of neural network architectures that have not been executed on existing infrastructure. And their interest was particularly in memory capacity and memory bandwidth. As they say here, because of the sheer size of the memory on a single chip, they can build models that they can't build as easily on other distributed architectures. And last but not least, we've also been doing quite a bit of work with commercial web and social media who are using large language models for text classification to drive services like search and question and answering. Many of these models often take days or weeks to train. For the customer illustrated here, they're using large BERT type language models that typically take them over 2 weeks to train on their existing GPU infrastructure. We took their code as is and ran it on a single CS1 and trained the same model on the same data set in under 2 days, which represented a more than 100x acceleration beyond GPU. And importantly for the customer, what this means is that they can not only run more training experiments so that their team can converge on the right model architecture to power their services, but that also once that model is in production, they can retrain it more frequently on the latest data so that their model better reflects the changing landscape of data that it's presented with in the real world. But of course, research and optimization doesn't happen in artificial intelligence alone. We've also been seeing a lot of interest and a lot of exciting developments in the research field around accelerated compute for HPC, and particularly HPC at the intersection with AI, where AI models may be used in partnership or in tandem with physics-based modeling and simulation to augment parts of an end-to-end modeling and simulation flow, or where AI models may be used to actually learn underlying physics and execute the actual physical model themselves. And CS1 uniquely has the power to accelerate both. A landmark first implementation for us was at Lawrence Livermore National Lab, where researchers at Livermore have installed and integrated a CS1 system with their Lassen supercomputer. This is one of the world's top supercomputers, and they're using this paired combination of the CS1 AI accelerator and their traditional supercomputing resources for cognitive simulation, where they're running physics-based simulations on Lassen that are driving output to the CS1 machine, which in turn is running high throughput, low latency AI models that drive data back to inform and direct subsequent time steps in the physics-based simulation. So this loop is a first-in-class deployment, as the CTO of Livermore Computing says. This heterogeneous HPC AI architecture allows them to have a compute volume that is specifically tuned and intended for machine learning models at the intersection of HPC. Just a few others that I thought might be of interest to this group. We've also recently had a very exciting deployment of 2 CS systems, so a dual node CS system cluster hosted by Pittsburgh Supercomputing Center, funded by the National Science Foundation, where we've actually just opened our early user program to early use in AI for science. We have early users there that are exploring CS1 for language modeling, sequence modeling, image and graph processing with model architectures ranging from BERT to UNet to LSTM-based RNNs, GNNs, and others. It's been tremendously valuable to us and our team and our systems to be exposed to sort of wide variety of real-world model architectures and problems. And as their PI says, together we're closer to achieving this vision of truly interactive AI research, where researchers can ask and quickly evaluate hypotheses around different models and data sets through the provision of this system. Outside the US, our system's recently taken a trip to Scotland, where we've deployed to Edinburgh Parallel Computing Center. The researchers there are using CS1 for language research and large-scale data science, or problems ranging from natural language processing to genomics and public health, as well as emergent research on COVID-19. Beyond the civil government and commercial applications, we're also working with the US Department of Defense. We're using both our systems for both HPC signal processing, as well as AI. In particular, one project is particularly interested in using our system for high throughput, low latency RF signal processing and emulation, where vast computational resources are needed to drive modeling and simulation problems that require real-time latency and extraordinarily high throughput for large multi-actor simulations. Last but not least, in the domain of strict HPC, we've also been working in partnership with the US Department of Energy's National Energy and Technology Laboratory, or NETL, where they're doing large-scale computational fluid dynamics. And they're together in partnership, we were able to bring up and demonstrate the performance of a biconjugate gradient descent algorithm for partial differential equation solving that showed 10,000x performance gain over GPU for this BiCG stab algorithm that's central to their computational fluid dynamics modeling code. So with all that, I'll transition. I think there may be a few questions. I'd just like to say thank you once again for the opportunity to talk to the group. I'm looking forward to learning more about your work and very excited to have the opportunity to introduce you to the Cerebras WaferScale Engine and CS1. We've seen some great progress with this across industries and application verticals, including scientific and academic research, where we're trying to accelerate teams' work by orders of magnitude. The CS1 shown at the right, this is our deployment actually at Argonne National Laboratory, is a machine that gives this order of magnitude performance gain, and importantly, also in a package that is programmable as easily as a single node. And it's also important to note, I think, for us that the WaferScale Engine in CS1 is a huge step forward, but is really just the beginning. We are soon to announce our second generation WaferScale Engine, which is going to be a big step up in performance and capacity over the first generation to even further accelerate our work together. So with that, I'll say thank you once again. I look forward to the opportunity to visit, and I'm happy to answer any questions you may have.
Okay, thanks for your interesting talk. And yeah, it was really interesting to learn more about these AI devices. And yeah, I hope to see you all at the next seminar.
Thank you.
Thanks, Andy.
Thanks, everybody. Take care.
Bye.